So, Chapter 1 of the course has been thus far about scientific method, units, unit conversions, the sorts of things that we need to have in our minds before we start doing physics. And with that covered, we will now move on to looking at physics concepts and utilizing the scientific method and all of the math and data stuff that we've talked about. If at any point the stuff that we have already covered is confusing or you need a refresher, again, never hesitate to ask me a question, because again, if something presently doesn't make any sense, it's only going to get worse if I don't address it now, because everything is going to build on everything else. As an example, the first concepts that we're going to go over in this course, beginning with chapter 2, are Newton's laws of motion. We're going to focus on the first one, shocker, first. But we'll also be using that to have a greater conversation about force and equilibrium, and then about motion as a whole. And this is a logical foundation for the start of the course, because things are going to be moving, and there will be forces acting on various objects throughout the entire semester. So again, as an example of how things build upon each other, if the first things we start talking about confuse you in any capacity, I want to know about it. I want you to stop and tell me, and I want to address the concern before moving on. So, as always, make sure to ask me questions when you have them. Does anyone have any questions before we take a glance at next week? Okay. Now, we are beginning the course with Newton's laws of motion. I mentioned last week that Newton's laws of motion are very good and very useful to physicists. They aren't perfect. I told the story about how they could not successfully track the trajectory of Mercury. My words are not working today. Newton's laws couldn't track Mercury's orbit in the night sky, proving that they were somewhat flawed. But they are still very, very useful. The only reason they couldn't track Mercury's orbit is because of, again, the space-time distorted gravity well of the sun, which is not something we have to deal with on the surface of planet Earth. So for all the motion that you will ever interact with in your normal life, Newton's laws of motion are very good, very useful, very accurate, and that's why we're beginning the course with them. Newton's very famous for his work on motion, and also very famous for his work on gravity. He was not the first person to talk about motion, and definitely not the first person to talk about gravity, because again, humans have been watching this happen for as long as we've been around. But he did get famous for it, and his math is very handy, and that's why we're starting the course off with it. The statements on the board are Newton's famous laws of motion. We will go over all of them in the following weeks, and I'll read through all of them now, at least briefly. At least the start of next week will be focusing on the first law and then how it relates to motion overall. Newton's laws of motion, you've heard all of these before, even if they aren't written or said exactly the same way. So all of these individual statements should still, I'm hoping, are review. Newton's first law of motion says an object at rest will stay at rest, or an object in constant motion will stay in constant motion unless acted upon by an outside force. This is very commonly referred to as the law of inertia. I'll define inertia later. And the law is referring to observations that you've made before, namely, objects do not spontaneously start moving on their own, correct? If an object, I'm going to use this golf ball as an example a lot because it's here. This golf ball is an object containing mass, therefore it has inertia compelling it to keep doing what it's already doing. This thing will not on its own spontaneously start moving. If it's currently sitting still from our frame of reference, it wants to do so indefinitely. And to get that to change, something outside of the golf ball has to imbalance it by exerting force on it. In this case, I am the outsider exerting force. But the object never does that spontaneously on its own. If the golf ball does ever start moving from rest, it's because something either forced it to move or something about its equilibrium state was changed outside of itself. If the table collapses out from underneath the golf ball, that's not the golf ball moving spontaneously, that's the table no longer being present to support it. Does that make sense? So, no spontaneous motion on behalf of the golf ball all by itself. Matter never just takes off randomly on its own. This does include your own body. You are made of matter, and your own body doesn't move spontaneously. There's muscles inside of yourself that exert forces on other parts of yourself to cause that motion. So you do not move spontaneously either. There are mechanisms in your body to create that motion via force. But the law also says that objects in motion want to remain in motion. So this law isn't just referring to things that are sitting still, it's referring to things that are currently moving. If something is moving, it wants to keep moving. For example, the planet we're standing or sitting on, Earth is constantly moving very fast through space, and it's going to keep doing that until something stops it, which hopefully doesn't happen. But other examples include driving, when you set your car to cruise control. Your car wants to keep moving in a straight line, and the only reason it ever eventually slows down isn't because the car wants to slow down, it's because friction forces it to do so. And when you set cruise control, you're telling the computer in your car's engine to output just enough force to overcome friction and keep moving at constant speed. The thing that we're going to cover going into Newton's first law in more detail is that whatever matter is already doing, sitting still or in motion, it wants to keep doing. Newton's second law then describes how to then change an object's motion. I've put this formula on the board before and I've described it as Newton's second law, but to review again, this formula says, using math as a language, and a net force, this is the Greek letter sigma, if you hadn't heard that one out loud yet, although at least 2 Greek organizations on campus use that letter. Sigma force, sigma in math means the sum of something, so the sum of all of the forces acting on something. I'm going to commonly call this net force, meaning the net lump sum of all the forces acting on an object. The net force acting on an object, the M part kind of represents the object itself because all objects have to have mass. The M stands for mass, represents the amount of matter within the object. If you exert a net imbalanced force on an object with mass, it will then begin accelerating. And accelerating is, by definition, a change in motion. We'll talk about the math for acceleration next week as well, along with the math definition for acceleration. But the main thing to note for right now is, if something is accelerating, its motion is changing. Acceleration doesn't necessarily mean it goes fast. Acceleration means change in motion. So right now, this golf ball is not accelerating. Motion is not changing. A car moving at constant speed is also not accelerating. Acceleration is any change in motion, either speeding up or slowing down. So objects don't spontaneously accelerate. To kind of combine these two laws together. Objects do not spontaneously accelerate. They have to literally be forced to. And that's what the second law says. Force causes change in motion in matter. And then the third law, which I think out of all of them is the one that gets said the most often in common English. For every action force, there's an equal and opposite reaction force. I actually find people tend to leave out the word force there. They often just summarize it as for every action, there's an equal and opposite reaction. But in terms of the way we write it for this class, we want to be very specific in saying for every action force, there's an equal and opposite reaction force. Another way I would summarize this as, if object A acts on object B, then object B is going to act back on object A. For example, I lean on the board. For me to do this, I am exerting a force into the board. Does that make sense? My body is pressing into the board. I wouldn't be doing that if I wasn't leaning on it. So when I lean on the board, I exert a force into it. So I am object A in this scenario, and the board is object B. The reaction force to this, according to Newton's third law, is that the board is going to push back on my body. So I lean on board, I push into board. The reaction to that is the board presses back out of itself on me. And I know that's happening because the board is keeping me from falling over. If I was leaning like this and there wasn't a board here, I'd fall, right? Right now the board is an outside force that is helping to maintain my equilibrium right now. This is true anytime any object acts on a second one. The second one will act back on the first. Same amount of force, just opposite direction, but also opposite targets. A on B, B on A. The two forces never act on the same object, they act on each other. Another example would be you guys sitting in your chairs right now. You press into the chair when you sit on it, the reaction is the chair presses back up on you, and that's why you don't fall on the floor. Anytime you exert a force on anything else, this happens. If you pick up golf ball, you push golf ball presses into you, and that's why you can feel it in your hand. It's pressing into your body's surface. A related note, well, sorry, words are hard and it's Friday. Story time. I did Taekwondo as a kid. And as a result, I actually learned a lot of these from my Taekwondo instructor and not necessarily from my physics teacher. Because I started Taekwondo at age 10 and I started physics at age 15. So I learned a lot of these from my Taekwondo instructor. Force is Newton's third law as it relates to martial arts. For every action force, there is an equal and opposite reaction force. If you punch something, it is going to exert a force back on your fist. And that's why punching hurts. Also, how martial arts relates to Newton's second law. Force equals mass times acceleration. If you want to hit something harder, you either need a bigger fist or you need to move your hand faster. So, occasionally I will give examples as they relate to Taekwondo. Just spoiler warning. These are the laws we'll be studying next week. On Monday, we will focus primarily on Newton's first law, describing forces in equilibrium states, how that then applies to motion as a whole. So next week will be Newton's first law, followed by all the descriptions of motion that we will use for this entire class. Then in the following weeks, we'll cover the other laws, different types of force, where they come from, what they do, etc., etc. Any questions at this particular time? All right, that's it for this week. Next week, do plan to start attending lab as normal, and have a great weekend. Stay safe, stay warm, stay hydrated. Where you go?
I was gonna say, if you just wanted to drive you, but I don't have these, I'll have to go to or just get off.
I'm sorry, because I have a note,
Oh, yeah, that doesn't.
but like the note is for, I don't know if it'll work for this today. We'll find out. No, you guys can do it.
I'm about to speak to the camera. I'm not speaking to any of you. If you missed class today, please let me know. We spent the first half of it doing an assessment. If you missed that, please let me know. You need to make it up. It's okay if you missed it. I just need to know about it. So if you're watching this after the fact, noting that it's short, what you missed was basically a quiz. Let me know. We'll figure out when you can take it. All right, cool.